So anyway, I promised we'd do some review this week. Not today. We'll finish 6.3 today. And I don't know if we'll actually finish it, but we'll do almost all of 6.3 today. And then Wednesday's class, we'll review. We'll do some neutral results, some proofs that I think could. I mean, they won't end up on the exam because we literally just did them. We will do them on Wednesday, but they're proof similar to things you might see on the exam. They're the right difficulty and so on. So they should be good practice. And one of them is something I promised to prove last time. One of them is something I'm going to promise to prove today, because we actually need them. But we'll start off with, I want to talk about lines. I want to talk about hyperbolic lines, distances between lines, and we're starting off with just the standard definition of distance that you've always had, that you're used to working with. Distance between a line and a point. And so distance between a line and a point is just drop this unique perpendicular from P to the line, and the length of that line segment is I should say unique perpendicular line segment. Just to be very clear that I'm not talking about infinite lines or anything. This is just this perpendicular line segment from the point to the line. This is the definition you're used to working with in Euclidean geometry. It still holds just fine in neutral or hyperbolic geometry. Why is this unique, by the way? I was tempted not to even write that word because to me it's kind of obvious that it must be unique. Why is there a unique perpendicular? What happens if I have another one?
This is a different distance.
Does that mean it's so that there's two parallel lines to repeat?
Are there two parallel lines?
Like, because of the, like, transversal making.
So this would, sorry, are you looking at L as a transversal?
So, like, a line through P parallel to L.
Oh.
Make it so that the perpendicular,
So you want to throw that in now?
so that those are right.
Oh.
Does that make sense?
I think you can argue something along those lines. I'm actually just looking at this triangle. Immediately I have a triangle with angle sum more than 180 degrees, and that can't happen either. But I think you can do something along those lines with a parallel up here too. So anyway, yeah, we have a unique perpendicular. I suppose then you'd have to argue why there was always one, but we've already proven that you can always do this. There is always one. So anyway, there's how we define distance between points and lines, and here's our big theorem about hyperbolic lines. Parallel lines are not everywhere equidistant. Okay, so this is obviously very different than Euclidean geometry, right? Euclidean. What happens in Euclidean geometry about two parallel lines? Well, you measure the distance between them everywhere. That's always the same, right? They're everywhere. They are everywhere equidistant. So they are everywhere equidistant. Meanwhile, hyperbolic is different from this. The distance between parallel lines is changing. What this does not say, and I want you to be careful when you're reading this, don't try and negate this statement. If I say they're not everywhere equidistant, that doesn't mean they're nowhere equidistant. Right? So parallel lines, you might have something like this. Here, the distance between the lines is the same, right? So they're not nowhere equidistant, they're just not everywhere equidistant, meaning if I take the distance here and the distance here, that's different. But the distance here and the distance here are the same, right? So be very careful when you're reading at this statement. So note, this does not say that parallel lines are nowhere equidistant. This may or may not be the case. This may or may not be the case. And somewhat interestingly, based on whether they're nowhere equidistant or not, we can actually classify hyperbolic parallel lines into two different cases. So, parallel lines, say L and M, come in two types. One is that L and M are indeed nowhere equidistant. And how does this happen? Well, in models, there's names for these things. These are usually called like limiting parallel or asymptotically parallel, and the names come out of what you see in the models. We haven't talked too much about the models yet, but generally what you'll see is these will be two parallel lines that want to intersect at infinity and nowhere else. So they tend to look like this. Right? And if you look at the distance between these lines, well, they are indeed nowhere equidistant, right? If you start measuring the distance between the lines, it's just increasing and increasing and increasing forever, right? So this is sometimes called limiting parallel, or asymptotically parallel, or quite a few different names because naming isn't entirely standardized in hyperbolic geometry. People have different names for different things. But the distance always increases. Distance always increases. So here's L and M. Or type 2 is the picture I already drew on the board to convince you that they don't have to be nowhere equidistant for this theorem to be true. You can still have some line segments between them that are congruent. So case 2, L and M have some really pairs of congruent line segments between them. So these look like the picture I already drew. L and M. And obviously this is different from the Euclidean case. They are not everywhere equidistant. You can see they're clearly sort of getting further apart and further apart in both directions. But they are somewhere equidistant, right? For example, just take these two those two line segments. Those look to me like they're the same length. Now the most standard word for parallel lines or pairs of parallel lines that come in this flavor are ultra-parallel. So, yeah, ultra-parallel. You'll also sometimes see hyperparallel. I don't want to use it though, because I've actually seen hyperparallel used to describe these. Like I said, the naming in hyperbolic geometry is not completely standardized between different authors. So usually people go with ultraparallel. And there's one big theorem here. I believe it's called the ultraparallel theorem or theorem of ultraparallel lines, which says basically that there is a closest point between these lines. It's the unique perpendicular between them. And it says that every pair of ultraparallels has a unique common perpendicular between them. And you'll notice, so what's happening in this picture? What do I have here? What type of quadrilateral is this? This is a security quadrilateral, right? I've got right angles here. These two sides are the same length, so I have a security quadrilateral in this picture. And yeah, we've already proven that if you take the midpoints and connect them, that is a common perpendicular. So anyway, let's prove this theorem. Let's prove that lines are not everywhere equidistant. This picture should sort of indicate where we're going to proceed or how we're going to proceed. Security quadrilaterals are really, really useful, so we're going to proceed using security quadrilaterals. And our proof will be a bit more enlightening than just this statement that lines aren't everywhere equidistant. The proof will illustrate really exactly what's happening. So, let's prove this. Let L and M be parallel lines. Let's say distinct. Let's be very precise here. Distinct parallel lines. And we'll choose 3 collinear points on L. And let A, B, C be points on L such that A then B then C. All right, so L and M. A, B, C. The textbook actually draws this same picture, but they draw them in an Euclidean sense with lines that look straight Euclideanly. I figure we're proving stuff in hyperbolic geometry now. Why not try to draw stuff that actually looks hyperbolic? So I've drawn 2 hyperbolic looking lines. And what I'm going to do is I'm going to drop perpendiculars from A to M. Or rather, I'm going to erect perpendiculars from M to these points if you want. So what do I call these? D, E, and F. I'm going to find a point on M so that when I erect a perpendicular, it passes through A. We've already proven we can do that. Same thing, find a point on M so that when I erect a perpendicular, it passes through B. We know we can do all of these things. And find a point on M so that when I erect a perpendicular, it passes through C. So let's let D, E, and F, let D, E, and F be the feet of perpendiculars from A, B, and C, respectively, And here's what I can't prove. I can't prove that they're all the same, or I can't prove that they're all different lengths. But what I can prove is that they can't all three be the same length. All right, so let's suppose they are. Suppose AD is the same length as BE as CF. So suppose they're all the same length. Then I have three security quadrilaterals in this picture, right? I've got, how about we label them using, these are the bases, so how about we call it DABE. Then DABE, EBCF, EBCF, and the whole big thing, DACF. These are all security quadrilaterals. Now, what does that mean? Do you agree they're all security quadrilaterals?
So
DABE.
would angle A,
Yeah, I'm fine with calling this angle A, but then it's what the hell is angle B, which side? So let's call it 1, 2, 3,
gotcha.
4. Yeah.
So 1 and 2
1 and 2 are congruent.
and 3 and 4.
3 and 4.
And then 1 and 4.
1 and 4. Yep. So angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. And angle 1 is congruent to angle 4. So by transitivity, I want to claim that that means angle 2 is congruent to angle 3. I can do that, right? Angle 2 is congruent to angle 1, angle 1 is congruent to angle 4, angle 4 is congruent to angle 3. So,
What was the word you used? Transitivity?
yeah. Congruence is a transitive relation. So, and it follows by transitivity of angle congruence that angle 2 is congruent to angle 3. But what's true about angle 2 and angle 3? They form a linear pair, right? So their sum has to be 180. If they sum up to 180 and they're equal in measure, then they both must be 90 degrees, right? But angle 2 and angle 3 form a linear pair. Hence, the measure of angle 2 is equal to the measure of angle 3, must be 90. I think you're going hard today. Where's the contradiction?
This would.
You can't have a quadrilateral.
Yeah, can't have a rectangle, right? That's the word. So can't have a rectangle, so Yeah, we've contradicted the hyperbolic parallel postulate. Therefore, any one of these, choose your favorite rectangle in this picture. D, A, C, F is a rectangle contradicting the hyperbolic parallel postulate. Not directly contradicting it, but contradicting a statement that we know is equivalent to it, which is that rectangles don't exist. So we conclude, what can we conclude? Our contradiction came from assuming this, that all three of these line segments are the same length. So our conclusion is that they can't all be the same length. So we conclude that it is not the case that AD is equal to BE equals CF. Again, be really careful on the logic there, right? The negation of this is not that they're all different. It's not that they're all not equal. It's just that they can't all be the same. So two of them can be the same, but they can't all three be. And that's good enough. All we were trying to prove was a very generic statement that they're not everywhere equidistant, and if one of these line segments is not the same as the others, not the same in length, then these two lines, M and L, are not indeed everywhere equidistant. But the proof is kind of enlightening, right? The proof is enlightening in that it really tells you exactly how these parallel lines work. It says if I have two line segments that are congruent, I can't have a third one in between that's also congruent. Right, so in other words, between these 2 points, or between these 4 points, or between these two line segments, the distance has changed. What's really happening is it's getting closer together. And I say between, but then you'll also notice that this means I can't have a third line segment anywhere that's the same length as these, because what if I put it out here? Well, if this is the same as this, now this guy can't exist. So I won't write down the details here, but this proof is illustrating sort of exactly what's happening with these ultra-parallel lines, is that if I have two line segments of the same length, there cannot be a third one. So there's really, in my mind, there's quite a few other things in this section. There's really only two more proofs I want to talk about, or two more theorems I want to talk about. I think we only have time to do one of them. But it has to do with triangles and circumscribing triangles. In Euclidean geometry, if I have a triangle ABC, let's see how much geometry 1 you guys remember. What is the circumcircle of a triangle?
Circle that goes through.
Yeah, the circle that goes through all 3 points. Where is the circumcenter? How do you find that?
The dot that is equidistant to AC and B.
Yeah, but how do you find it? Like it's in particular, it's the intersection of three lines. Which three lines?
You find
Is it there,
a
the perpendicular bisectors?
It's the perpendicular bisectors of all three sides, yeah. So you find the perpendicular bisectors of all three sides. Those intersect at a point, and there's the circumcenter, and the circle is, of course, yeah. Okay, so in Euclidean geometry, the important observation is in Euclidean geometry, every triangle can be circumscribed. Every triangle ABC can be circumscribed. So the question is this true in hyperbolic geometry? And the answer is no. Answer, no. Which again is somewhat surprising. You would sort of, I think you would expect this to be true. It's just so natural in Euclidean geometry, but in hyperbolic it's unfortunately not true. Again, I want to point out that the answer of no here is not saying every triangle could not be circumscribed. In other words, there are no triangles that can be circumscribed. That's not what I'm saying. I'm saying that there exists at least one triangle that cannot be circumscribed, right? So I could state this as a theorem right now that not every triangle can be circumscribed. But how about we just go through a construction and then we'll state the theorem. We'll go through a construction that shows that this can't always be done. In other words, what I'm going to do is construct a triangle and hopefully convince you that this triangle cannot be circumscribed. It's we're going to end up with a lot here. So consider the Security Quadrilateral. A, B, C, D as drawn. Let's see. I won't attempt to draw this in a hyperbolic sense because it will get pretty messy. A, B, C, D. Leave some space above it. We're going to continue this picture above, so it needs to be some space. AD and BC are the same lengths. And let's throw in the midpoints. Throw in the midpoints here. M and N. Okay, so and let M and N be the midpoints of A, B, and C, D respectively. What if I connect them? Well, we actually showed this. I think this was one of the very first things we ever proved about security quadrilaterals, is that the line that passes through the midpoints of both of these, both the base and the summit, that is the perpendicular bisector of the base. And And we also had by SAS, so these two are congruent. Because this is linear, those must be right angles as well. So we'll just complete the picture. I think we've proven that stuff. Okay, so here's my claim. And like I said, I was going to defer another thing until tomorrow's class. But my claim is that AD is greater than MN. Shouldn't be hard to show, but so my claim is that this side must be longer than this segment joining the midpoints. Again, if they're equal, what happens? If they're equal, this is a security quadrilateral. This is a right angle, so I've got rectangles, so that can't happen. You just have to show it can't really be greater. But in any case, we'll prove this next time. So we'll just accept that for what we're doing. All right, so let's let E be a point on this extended ray MN such that M, then N, then E, and such that ME is equal to AD. Okay, so I'm just saying, let's extend this ray. Let's extend this ray MN, let's extend this ray out to a point E. So that ME and AD are the same lengths. So E is not M, right? This has to be some non-zero distance. So DCE forms a triangle. Since E is not on the line segment DC, we have a triangle DCE. Do you believe that? It's actually it's somewhat subtle. You have to really go back to all of our postulates. Why can't E be on DC? Well, because DC intersects this line segment at N. E is not N, meaning if E was on this line, we would have a line that intersects another line twice, and that can't happen. Right? Every line intersects at most one. Every pair of lines intersects at most one point. Okay, so we have this triangle. We'll keep going. So next, let Q and R be the midpoints of AM and DE. AM and DE respectively. So Q and R. what am I going to claim? Well, I'm claiming that we've built more security quadrilaterals in this picture. So, since, what's a security quadrilateral? AMED. Since AMED is a security quadrilateral, do you believe that? AM, here's my base, I have two right angles on the base, and we constructed E so that ME is the same length as AD. So these two sides are the same length, which means AMED is indeed a security quadrilateral. And that means that QR is a perpendicular bisector of AM and DE. So since AMED is a security quadrilateral, it follows that QR, we'll just make this a bi-infinite line, is the perpendicular bisector of the summit and the base. All I really care about is the summit though, so we'll just say it's a perpendicular bisector of DE. Let's do the same thing on the other side. All right, so similarly, let's call it S and T. S and T, choose those to be the midpoints. Once again, I have a security quadrilateral, MBCE. So S and T form the perpendicular bisector of CE. So similarly, construct, I don't want to use construction language, let's just say similarly we have. And I don't want to indicate I'm getting out a compass and straight edge or something here. Similarly, we have the perpendicular bisector ST of D, we'll call it T. Of C. Where's the contradiction?
Definition we started class with.
They're parallel.
Are they parallel? Yeah, they would be parallel. These are parallel because they're both perpendicular to the same line. Alternate interior angle theorem comes in, so those are parallel. Let's say because QR and ST are both perpendicular to AB by the alternate interior angle theorem, we have that QR and ST are parallel. And this is a contradiction. Well, it's not a contradiction. I haven't actually assumed anything to come up with a contradiction. But what it does tell me is that, well, suppose I could circumscribe this triangle, ED and C. Suppose I could somehow do that. Where would the center be? Forget about all this stuff. Where would the center be? Well, the center is equidistant from E and D, right? Since both of these 2 points are on the circle, the center is the same distance from E and D, right? So the center would have to be on the perpendicular bisector of E and D, which is this line RQ. Similarly, it's the same distance from E and C, so the center would have to be on the perpendicular bisector of E and C, because it's equidistant for both of them, while the perpendicular bisector is this line here, meaning it's got to be on both of these parallel lines simultaneously, which can't happen. So a bit to think about there, but there's a conclusion. So now, if triangle EDC could be circumscribed, if it could be circumscribed, its center would have to lie on QR and ST, which is impossible because they're parallel. Which is impossible because, sorry, it's really hard to write this low on the board, but they are parallel. Right, do you understand that? If I could circumscribe at the center of the circle, being equidistant from all of these points would have to be on the perpendicular bisector of the chord that joins them, or the triangle edges. So it has to be on the perpendicular bisector, but we've shown that these two perpendicular bisectors are in fact parallel. It can't be on both of them at the same time, so no such circumscribing circle can exist. So yeah, what were we proving? Well, we never actually wrote the theorem, but this shows that there exist triangles that cannot be circumscribed. And we actually showed how to always build one, right? Take a security quadrilateral, cut through the midpoint, extend that midpoint up so that this line segment is the same length as both sides of the security quadrilateral, and there's a triangle. So we showed the following. Theorem in hyperbolic geometry there exist triangles that cannot be circumscribed. So some triangles cannot be. There's one more really important theorem in this section that I won't get to today, but it tells us, remember the converse of the alternate interior angle theorem says if I have two parallel lines and I cut it with a transversal, then alternate interior angles are congruent, right? That's the converse of the alternate interior angle theorem. the theorem I want to talk about tells us exactly when this does happen in hyperbolic geometry. So when you're guaranteed that when you take two parallel lines and cut them with a transversal, when you're guaranteed that that happens. But I guess we'll postpone that until next week, because on Wednesday we'll do some review. So we'll stop here, and yeah, I'll see you Wednesday.